Okay, so we last webinar had a look at this information here, and we were able to understand last week that when a current flows through a wire, it itself generates a magnetic field, and we used our thumb up to do the direction of the magnetic field around that wire. So this here is the direction of the magnetic field around this wire. We understood that the field lines, magnetic field lines, go from north to south. They're south-seeking in a permanent magnet. So when we have that interaction between these two magnetic fields, we get this catapult effect here. And what that essentially does is we get the bunching up of the lines, and this then pushes forward in this direction is the force. And we used Fleming's left-hand rule, where this is the force, this is the field, and this is the current, okay? And we were able to predict which way the force would go. All right, and then when we talked about it, we took it a little bit further, and we talked about the electric motor, and we understood that if we had a coil of wire coming round here, we've got a current flowing up and a current flowing back, and that is going to change the direction of the field around that wire. It's going to flip it by changing the direction of the current, and so in doing so, we are able to get going up in one direction and back down in the other, the force in the other. But this was only rocking it backwards and forwards like this. So we needed something else, and those little bits that we talked about, a couple of extra bits that you had to add to it, and it was the one that I wasn't very good at pronouncing, the commutator. And these split rings here switched the polarity, which is the essentially the direction of the current every half turn, so it continues in its same rotation around. And we have these brushes here that ensures that you've got that constant connection to a current. So that was the principle that we looked at of the simple motor. What we then went on to, let me have a look, sorry, my slides have got ahead of me. And then what we didn't look at, because it was triple only, is how we apply that to loudspeakers. Okay, so here we've got the key principle with a loudspeaker is you've got an alternating current, which means the current reverses backwards and forwards, backwards and forwards. And so if you've got that current that is constantly changing direction, you've got those changing in the magnetic fields. I'm sort of demonstrating this with my thumb up, thumb down at the moment. The direction of the field around the current changes as well. So we've got this possibility then of movement backwards and forwards, backwards and forwards. And in point of fact, one of the questions that you did this week was about how if it's moving however many times a second, what is that frequency, and that's what that can cause. Now if we've got something quite lightweight here, like a paper cone, and we attach this to here, what we're creating is some backward and forward movement here, backwards and forwards, backwards and forwards. And we recognize that backwards and forwards as a wave. And the wave that it is a longitudinal wave. So we've got that here, which I put in. From our work on sound waves, this up and down movement sets up the longitudinal wave with those oscillations or vibrations that are parallel to the direction of the movement of the wave. Okay, so we've created a sound wave that is coming out from here. Now, from our work that we've done on hearing, we know that the ossicles, it hits the eardrum vibrates, then you've got the ossicles on the inside of the ear, then you've got the cochlea, and inside the cochlea with the semicircular canals, and inside there you've got the little tiny hairs, and they vibrate very, very slightly, don't they? And that then is converted to an electrical signal that connects it to the auditory nerve, and then is processed in the brain. So this is, I guess, sort of end to end, where our understanding of waves can move into, and where a question might be around work on waves, but then moving into how does a loudspeaker work? Okay, so that is trying to join up the dots for you that you've got on there. Okay, I can see I've got no questions so far on that, so that's fine. Okay, here's an example of a question on it. It says the loudspeaker cone vibrates when an alternating current flows through. Why is this? So the current flowing creates the magnetic field. This interacts with the permanent magnetic field. Okay, and that produces a force. Now we recognise that as essentially the same answer as a motor effect question. They're exactly the same. The words, the language that's being used is exactly the same. So you don't really need to learn anything new to answer these questions. It's all about when a current flows, a magnetic field is induced, and when that interacts with another permanent field, then there's going to be a force. The extra bit here is that obviously the current is changing direction because it's alternating, so that then causes the force to also move in the opposite direction. Okay, so that is just enforcing, in point of fact, your understanding of the motor effect. Not much more to add from there. Now, we're going to move on to the triple only stuff that we've got going on, the last bits of the electromagnetism with triple only. It's quite dense. These PowerPoints are quite information dense, so I really hope that you've had a little look through with them first, and you might have a couple of things like, oh, I wasn't sure about that, and you'll know to pay attention particularly. Now, this sits very nicely with the work that we did on P1 of the National Grid. So from the national grid, we recognize this, okay, and that we've got this step up transformer here, and basically what we learned at that was that we step up the voltage, okay, and it means that the current can be reduced, and if we reduce the current, then there's less, it's more energy efficient, there's less resistance going through there, so you can carry a massive amount of voltage, you know, without losing too much along the way. This is the equation that we use to recognize that if I step up the voltage, then the current has to go down, because we're here at a power station, and power equals voltage times current. Okay, so that is the relationship between them. The converse happens at the step down transformer, so we're reducing it to 230 volts, which is essentially coming into our houses. This is the bit we do. We don't really talk about factories at GCSE, but obviously they are going to have more power having to be transferred over there, more voltage coming into them for what they're doing. But in our homes, it's 230 volts, which is, I'm hoping, what you already knew from your work on P1 with that. So let's think about then what is, how do we generate electricity? This used to be everybody, but it's now only triple only, actually. And so we know, let's think about what we know, and then we can obviously conclude that the opposite must be true as well. We know that if we have a current flowing through a wire, that it generates a magnetic field. So actually, it must make sense that if we have magnets that are moving near a coil of wire, then electricity would be generated. Okay, so if we have, and the way that if we were in school, we would demonstrate this, is that we'd have this solenoid here. Okay, and we would push, you can push through a permanent magnet, a bar magnet, through the centers of the solenoid, and actually you can get a reading on an ammeter, very low reading, excuse me, I need to put my phone on silent, a very low reading on an ammeter. Not much is, you know, the current is not much potential difference that's been induced there, but you can get a reading from that. Okay, so what does that mean? It means that this is how electricity is generated in a power station, but obviously on a much larger scale. You need something to move in the first instance. Okay, you can't get energy from nothing. You know, it doesn't just sort of come, you've got to harness that energy. So it might be the wind turbines, it might be, here we've got water turbines, it might be most commonly burning fossil fuels that heat up water, that then evaporates to form the steam, and those turbines are turned from that. That's how we get the motion part of it. We need the kinetic energy. So that turbine then is turning from that, and that then spins magnets, okay, inside these copper wires, and the size of these are about the size of a bus in a power station. They're enormous, they're absolutely enormous, and so you can imagine from that happening, we are now going to get an electrical output through these signals here. Okay, so let's read the bit that I've written here. The movement of a magnet inside a coil of wire, a solenoid, induces a potential difference in a conductor. By conductor, I just mean in a wire. And if the circuit is complete, a current will flow. This is how electricity is generated in a power station. So in a power station, we have got the magnets that are spinning, and the way that the magnets spin is that the turbine is turning those magnets. You need something. Energy is being converted from kinetic energy to electrical energy. Okay, and this is how we would do that in school. We have generated electricity. Okay, the generator effect. So, also, if it doesn't have to be just the magnet that is moving, it can be the coil that is moving. Okay, so you'll recognize these diagrams because they look similar to the ones that we had on slides previously, but we've got something now to turn this. We're not trying to turn it using an electricity. We want to make electricity. We want to generate, induce a potential difference, induce a current to flow around the circuit. And so if we now move that coil of wire by using a turbine, something that will turn it for us, we can now induce a potential difference through that circuit, and electricity will flow. Okay, so from last lesson, we understood that placing a conductor, a wire, in a magnetic field when it is switched on induces a force. Nothing switched on and not moving, nothing at all. Okay, so switching it on made the magnetic field, and then we had the interaction here from the motor effect. Now with the generator effect, if I have nothing, yes, a complete circuit, but it's not connected to a power supply, if I am using a turbine to move this coil, it will interact with the wires, or sorry, the field lines of the permanent magnet. I'm pushing it through these field lines backwards and forwards, or rotating it round. Okay, and that then causes an induced potential difference within that coil of wire. Okay, it's an alternative way to generate electricity, okay, than the one of moving the magnet. But in fact, the same things are happening. We have to make the magnetic fields essentially move, don't we? Either through the wire in some way. So it's kind of like you could either do magnets moving, or you could do the wire moving. Okay. Let me just see. No questions have come up for this one. So, if a current is now flowing through the wire, that means it is now producing its own magnetic field. That magnetic field is going to interact with the magnetic field of the permanent magnets. We say, and this is all you need at GCSE, it does come in at A level, where we use Fleming's left-hand rule, and at A level you'll bring in Fleming's got a right-hand rule, but I'm not going to go through any of that today because it's nothing to do with GCSE. This is the bit in red that you need to know, okay, that the induced current always opposes the change that made it. Okay, and so that is the statement that we say about an induced current. It opposes the change that made it. Now, to change the size of this induced current, or induced potential difference that we've got here, you effectively need to change the rate of the changing field, i.e. you need to do this a bit quicker, yeah, or slower from here. So you can either increase the speed of rotation, increase the strength of the magnetic field. Those are the two most common ones you can use, but you can also increase the number of turns in the coil of wire. So here, for example, if you have loads of turns of coil of wire and you're pushing the magnet through, then, and that's the option for you, then obviously you're going to create a bigger induced potential difference. Okay, let's just check. No questions come up so far. Oh, one. Can I read it? No, I'm going to wait till the end on that, so hold through with that one. We've got this, but now we need to look at this idea of being able to generate electricity. That was the first bit that we've talked through. Okay, so we've explained how to induce potential and what the generator effect is. We induce potential by moving either a magnet in a coil of wire or by moving the coil of wire through a magnetic field. That's how we induce potential. And this phenomenon is called the generator effect. So we're going to take this a step further, okay, and look at the two types of generators. There's an alternating generator, an alternating current generator, and there's a direct current generator. Okay, and we're going to go back to our little friends here, okay, that we've got at the bottom. Okay, so the first one that I will look at is this alternating current generator, which is called an alternator essentially. Okay, we've got here actually, do you know what? I'm going to talk through this one. Apologies, I'm going to talk through this one first. We recognise from our work on the motor effect that we don't switch on the current here. We recognise this. This is exactly the same, which is what we did with the motor effect, but there's no current flowing through here. Okay, if there was a current flowing through here, we would be able to rotate this. Okay, by the interaction with the field. This is already rotating. Because it's attached to something that is rotating it, which is what your steam or your wind turbine or something like that. So it's all connected up. It's all connected up. The circuit is complete, but there is no sort of battery power supply. The power supply is the turbine that is already turning this. So we've got an input energy of a kinetic energy here, and the output energy here is going to be electrical energy. So as I turn this, okay, and I rotate this round, we have these split ring commutators here. Now their role previously, okay, was to flip the polarity coming from a power pack. But now what they're trying to do is essentially rotate, they flip around to keep the current going in one direction only. Okay, so these things are still the job of the commutator is the same thing in each scenario, but rather than flipping the current around, you know, to go in, we're now making sure that it goes in one direction on the way out. Okay, here this is exactly the same principle. So we've got our turbine that is turning the coil here using kinetic energy, and here we've got, these are called slip rings. Okay, not those split ring commutators. So can you see this line here? We can see it's split, and this is just all the way round. This means that every half turn, the current will switch. Okay, because it's just providing a continuous flow of electricity coming down, and as it's passing on one way, the magnetic fields are going in one direction, and when it comes back the other way, the magnetic fields are going in the other direction, and so essentially the current is going backwards and forwards, backwards and forwards. The coil always turns in one direction because it is attached to the axle, and the kinetic energy source is moving it. So we always have the coil flowing in one direction. It's always a movement in that direction there. Now, if you're going to look at these on a sort of transfer them into an oscilloscope, okay, in P1 we said that this was a direct current. Okay, so the potential difference didn't change over time. And we said an alternating current looks like this because the potential difference reverses, okay, backwards and forwards over time. The national grid, recall that the 230 volts and a frequency of 50 hertz, so it's moving 50 times a second, backwards and forwards. And that's what we have from the national grid. Now, if using our little dynamo generator that we've got, there is going to be a peak point when potential difference is at its maximum at some point during that turn, when it's absolutely perpendicular to all the other field lines and it matches up perfectly. We've got a peak potential difference here, but obviously because it's doing a rotation, it's not going to stay peak the whole time. Okay, so it will drop back down, but it will never reverse. It never goes below the line. So a DC output from a dynamo gets this sort of like M shape here that is going through, that never goes below the line, but it fluctuates because there is an optimum point in the turn of the coil where everything is perfectly matched up with the field lines going through. Okay, and in fact some of those questions were asking, weren't they, about like a magnet that might be slightly offset. How can you make sure that you can reduce something or increase it? And it's about making sure that everything is perfectly lined up, and that is what this shows here, that at this point, at these tops here, everything is perfectly aligned. Here we look, don't we, and we recognize that actually this looks no different from this. Okay, it's an alternating current. There is going to have a peak, same principle, because when it's turning at both points, it will have that optimum. Everything is, you know, as good as it can be. So let's just read this little bit here. This oscilloscope trace number 3 shows that there is a peak point in the turn that a maximum induced potential difference is achieved. But because of those split ring commutators, the polarity switches, so the trace doesn't go below the line because the current is switched every half turn, so it never reverses. Okay, so those split ring commutators, their role is to switch polarity. That is the job of that one there. And if that is because in the generator effect, because the coil is already turning, you're not trying to turn a coil, you need to switch the current within that coil itself. You're not trying to move it backwards and forwards. But in a motor, it would naturally move backwards and forwards, but you use those to switch the polarity to keep it going round. So that's just the role. A split ring commutator switches polarity. Okay. Here 1 and 2 are showing the alternating current every half term from a max potential difference in one to a max potential difference in the other. Okay, and remember how we can get the difference here between the two. We can increase the speed of the rotation, which we've done here. We've increased the strength of the magnetic field, okay, at that point here. Now, before we move on to transformers, let's just review this again. I'm being deliberately here going back over and over and over. And in point of fact, I'll say at this point, I'm going to push out invites to tutorials as well. I'll put something up through the classroom that you can sign up for, that we can talk through it again as well. It's not because we're not going to do it in September, but I think if you really understand it now, come September, you'll be flying, absolutely flying, okay? So let's sort of look at these ones that we've got. So we've got the motor effect. Essentially uses electricity to generate movement, electrical energy to kinetic energy. Current in a wire produces a magnetic field that interacts with the magnetic field of the permanent magnets. Those interactions cause a force on the conductor. Typical answer to a 3-mark question that many of you got absolutely perfect in those exam questions. Fleming's left-hand rule is used to predict the direction of the force on the wire. By creating a loop of wire, the current flows in different directions. And then we've got here, those split ring commutators are used to keep the coil spinning in the same direction by changing the polarity of the current. That is the information that you need to know about the motor effect, okay? The next one we've just been introduced to is the generator effect. So here we are inducing potential difference so that a current can flow. We are transferring kinetic energy into electrical energy. Using a source of kinetic energy, which would be your wind turbine or burning your fossil fuels or wave or whatever it is, using that source of kinetic energy, either a magnet can spin inside a solenoid, moving backwards and forwards like it is on this one here, which is what they use in power stations, or a coil of wire can spin inside a magnetic field. This phenomenon will induce a potential difference in the wire. A current will flow. Next one. Okay, so now we understand what the generator's effect is. We can get either direct current or we can get alternating current by using those little extra bits. Okay, so in the direct current we use the split ring commutator, which switches the polarity every half turn, so the current is staying in the same direction. This setup looks exactly the same as the motor effect. Okay, the difference being one has electricity that is providing the energy, and the other is kinetic energy, okay, that is providing the energy to make the electricity. But remember, that's that there is a source of energy that is spinning the coil of wire, so the magnetic fields generate electricity. The split ring is used to control the direction of the current, not the force of the conductor, like the motor effect. Split rings achieve both of these things by simply switching polarity. And then we've got the alternator, which have those slip rings, which essentially means that the polarity does also switch every half turn. And so we get a trace that looks like this. Just checking. Okay, everybody seems to be with me so far. So now we're going to look at transformers. Okay, and this is this bit here. What's going on in this box here and here? And transformers are essentially, this will please some of you, and some of you will feel a bit more, it's basically maths, but it's not difficult maths, it's ratios. Okay, so the key principle is an alternating current through a primary winding. Okay, so this bit here induces a magnetic flux in the soft iron core. Well, we've seen that because we've done electromagnets. Yeah, this is electromagnets here. So, but if we have it in this shape, then this magnetic field will go back on itself, won't it? Now, if it's an alternating current, it will only work. It has to be an alternating current through here. It can't be a direct current, and I'll explain why in a minute. But because so what we've got here is a coil of wire and a magnetic field. That's not going to set up. That's not going to set up a current here. It can't. Remember, because you've got to have some movement. So if I put through an alternating current here that is going backwards and forwards, I'm getting this flux here as well. And so this flux here can then induce potential in this wire. Okay, these are totally separate circuits, but I'm using magnetic field, the principle of how electricity interacts with magnetism, to essentially induce my current here. I am doing the equivalent of this. Okay, this in here, this magnetic field here, we're moving it backwards and forwards because we're physically moving the magnet. Here, the magnetic field that is being set up by this, because this is iron, this is an iron core, it's not a magnet, it becomes magnetic. Okay, this magnetic field that is being set up by my electrical current here is basically stopping and starting, isn't it? It's going backwards and forwards. It doesn't, you know, there's movement in this magnetic field line. So this then sets up an induced potential on this one here, and my current can go through. So I could do it, but what we'll notice here is that I've got a lot of coils here and fewer coils here. Now this is where it's actually really quite clever and also very simple. It's very simple. It's Faraday's law. Those of you that go on to do A level will go into this a lot. From a power station, the power coming out of a power station does not change, okay? Remember, power equals current times voltage, or voltage times current. Power doesn't change coming out of here. All the power that is leaving my power station is going to come round into my homes, hopefully not losing any through resistance on the way, or heat loss and things like that, very minimal, and we always assume 100% here, okay? So what changes is the voltage, the ratio of voltage to current, okay? So coming through here, at this point, I've got a primary current here. So let's work through this. I've got a worked example here of a step-down transformer, which is what this is. Okay, we can tell that because there's more here and there's fewer here. So in here, if I had, say, 10 turns, 10 coils, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way down here, and then I had 5 here, okay, where n equals number of turns, okay, of the primary one here, NP, so that equals 10. The number of turns, the number of coils that I have in my secondary one equals 5. So my ratio is 2 to 1. I've got twice as many here as I have here. Now, what happens is the primary potential difference here is going to be twice as large as it is here. So I start off with 400 voltage coming through here, and here I end up with 200 voltage. So what's changed? Power's not changed. At this point, my current has increased. Okay, I've stepped down my potential difference, but my current would increase. It's going to go faster. So P for power equals the same. And if we look at this this equation, which you need to know, is that essentially it's a ratio. Okay, that if I divide the number of turns in my primary winding and I divide it by the number of turns in my secondary, it is equal to saying that the voltage in my primary wire is divided by the voltage in my secondary wire. The ratio is the same. This is, when I said it's all about maths, that's essentially what it is. We understand the principle that you've got to have an alternating current to go through so you can induce potential difference here, and how much you induce is a ratio to the number of coils that we've got here. I can see somebody's just asked a question on this. I can't without getting rid of my screen and then not being able to get it back again because it's just me on here. I've only got a few more slides, so I will answer that question at the end that has come up. So what does it look like in reality? Electric toothbrush charging bases, okay, if you ever wondered how they work, because obviously you've got two little plastic coatings on there, essentially, haven't you? The electric toothbrush is charged by standing it on a separate charging base, and this is how it works. So I've got my charging base here, which is connected to my alternating current 230 volts main supply. Okay, so that here I've got my iron bar coming through at this part here. Okay, and that then is going to set up on the base of my toothbrush a secondary coil of insulated wire inside this toothbrush itself. Now we can see that this is going to be lots of coils to a few coils, so it is definitely going to be a step down. I do not want 230 volts going through here. I need to be it needs to be much less than that. So hang on, let's just move my face out the way here so we can see all the questions. So an alternating potential difference across the coil in the charging base creates an alternating current of the coil inside the toothbrush. Explain how. So an alternating current through the primary coil causes a changing or an alternating magnetic field around the iron bar. We've got this movement which induces an alternating potential difference in the secondary coil. Okay, so that was the key idea as to how this works, this thing that if we're moving this magnetic field here, that I am going to induce potential. That's the principles behind the generator effect, essentially. But what the transformer does is it takes ratios of coils. So when the toothbrush is being charged, the potential difference across the primary base is 230 volts. The charging potential across at the second base is 7.2 volts. Here I've got 575 turns. How many have I got here? Okay, so how do I go about answering one of these questions? Some of you will have done this and understood this already, but I'm going to go through it quite simply for this. Okay, it's about ratios. So always start, unless of course you can do it straight away in your head, but actually you should really always write it down anyway, because in case you make a mistake, it's, you know, just to be sure. This is the mark scheme here, okay, but this is my working through it. So I've got NP equals 575, because that is the primary coil with 575 turns. I need to find out what value I'm going to put up here. This is what they're asking me to find out. But I know that this sum is equal, the answer of this sum is equal to the answer of this sum, essentially. Okay, so there's a ratio involved. So if I have 230 here, okay, with my volts here, and 7.2 here, because that's the other value that's been given to me. If I divide these, the sort of like the factor is 31.944. So that essentially is my value that I'm going to be using here. So if I have 575 divided by 31.94, I equal 18. Okay, it's how I work out what that is here. Okay, so if I do that sum, then that is what that comes out to. Is there another one? Here's another one. The national grid, in the national grid, and this is, oh, I did this because this is your key here, a very large step up transformer. So that tells me that this is going to be something that is, you know, I'm going to have a big difference at this point here. Transformer, link power stations to transmission cables. A transformer used for this purpose has 800 turns on its primary coil and 280 turns on its secondary coil. The potential difference across its primary coil is 25 kilovolts. Okay, now what do we remember about those? The K stands for, I need to chuck on another 3 zeros on it. Okay, that's what that means there. Use the equation in the box to calculate the potential difference across its secondary coil. Show clearly how you work out your answer. So using the same understanding of what I've done before, where am I putting my numbers with respect to these here? How can I put any of this descriptor, I want to put a value next to it and see what one is missing. Okay, so I start off with the first thing that's given to me. A transformer used for this purpose has 800 turns on its primary coil. So at this point here, I'm going to write 800, which is what I've done here. And it has 12,800 on its secondary coil, which is here. So this divided by this is the same as this divided by this. So the first one is I've got 25 kilovolts. Okay, so I'm just going to reduce it down to 25 at the moment. Okay, to make that a value from here, divided by something. I work out my ratio. So this one divided by this equals 16. Okay, so the ratio is that this value here is 16 times bigger than this value. That's what that means. So this value here has to be 16 times bigger than this value. Okay, that is what I'm talking about when I mean a ratio. So you need to work out that that is 16 times bigger, and you do it by doing this bit here. So the ratio is 1 to 16. So if I have 25 in this one, I have to have 400 kilovolts or 400,000 volts in this one here. Okay. And the last bit that we are going to go through is using power equals potential difference times current, P equals IV. The power transferred does not change. Okay, so the power stays the same. What changes is the ratio of voltage to current. Okay, so this value times this value is always equal to this value times this value, but these values are going to go up and down, and we do that, don't we, because we can transfer more energy without losing any. We want them to be as energy efficient as possible. So the worked example is a step-up transformer is used to, a step-down transformer is used to step down an alternating potential difference of 230 volts to 12 volts to supply electricity to a 12-volt 2.5 amp device. Okay, so calculate the current in the primary coil of the transformer assume the transformer is 100% efficient. Okay, so the transformer, just for advice, I don't think I've got one in here now, is when you plug in your laptop or your Chromebook, there'll be sort of like a bit of a box on it, won't there, when you plug it in, or maybe it's in the wire and you've got a little thing. That's your transformer. That's basically stepping down the current from the house to whatever it is the current needs on your device that you're working from, and they're really quite common on laptops and electrical devices and stuff like that. That's where they're attached to. Okay, so let's look through this question again. First thing is, let's write out what we know. Let's insert and figure out what we're trying to do. So we've got 230 times question mark. So this is my primary voltage, my primary potential difference that's coming through with a current that I don't know. But that current, this value is equal to this times this. So I know that that this is 12 and this is 2.5. Okay, so it's what did I do here? Well, I times those together, equals 30 here. Yeah, so 12 times 2.5 equals 30. So now I've got something where I can easily make this the subject. Okay, I make this the subject by keeping this here and bringing my 230 over the other side. So 30 divided by 230 equals 0.13 amps. That is always going to be lower than this value. If you've got a value that was higher, then you know that's not correct, is it? Because it can't be. Okay, it has to, these two things have to equal the same. So it's your double check, and you can always just do them afterwards. So if I do that times that, I get a value here, and if I do this times this, I get a value here. As long as those are the same, you've got the question right. Okay, I've talked through loads. I've talked through absolutely loads, and I'm going to push out, as I say, some tutorials on this next week. What we're moving to is sorry, hopefully you can't hear that too much. I've got some building work going on in my house. I'm downstairs. We're going to go through some, stop screen sharing. There we go. We are going to go through some tutorials in the enrichment lessons that we have. So from there, we'll be able to do some little tutorials. We can go through this, and I'll give you some more exam questions, and we can all practice them. There'll only be about sort of maybe 6 of us on a go, and you just sign up, and we can do all of that. Okay, so I've got here, can you give an example of a current opposing a change that made it? Oh, right, so that was the one when I said that's all that you need to know from it. That is just any of those examples that we had. I wonder if I can go back onto screen sharing here. Perhaps I can. Okay, so I went through, didn't I? And I said the only thing that you need to know here is the induced current always opposes the change that made it. All that means is that when you get that that current flowing, okay, the direction of that current, the way that it flows, is that it always opposes the thing that it induces to it in the first place. For example, if it's going to be pushing in one direction, it wants to push back in the other. Okay, that's just the phenomenon of it, and you would use Fleming's right-hand rule to sort of prove that law of it. It's one of the things that they've stuck in this sentence. Really, it's just a sort of, oh, look, we better make them say that. Okay, so that's the bit on it there. What I will try and do, I'm not doing exam questions this week, I'm doing on this, but when we do these tutorials, I'll try and find some exam questions that where you would insert that statement in, so you can see what they look like. Okay, I had another cue. Oh, I've got to stop screen sharing. Another question. Where does okay, that's not very helpful because I don't know which one it was on. Where does the 200 potential difference go? No, not sure about that one. Sorry, you'll have to send me another one with that. Any more questions that anybody else wanted to write up with it? It's loads to go through. I want you to get to a stage where you understand the principle of it, you sort of recognize what the key bits of information are, so you can, you know, these are my salient points. I have to say these things every time I answer the question. And if you get to that stage, when we come back to look at it again and we revise it in year 11, actually you're in a perfect position, because you understand it now, you kind of forget, and you need to get to the point where you've almost forgotten it, and then we'll come back in and we'll do it, and it'll be really well reinforced. So actually it'll be something that you'll be really quite confident with. What I'm really keen for us to be in a situation with is that we've gone through this physics. We're kind of like, we're okay with most of it. We think we're okay, but we just want to check that we're okay. And obviously you're answering the questions, and some of you, you know, you're doing absolutely amazingly. I'm really impressed with what you've done. And so you already know that you're kind of okay, but there's probably quite a few of that I think, oh, I think I know, but I just need that reassurance. And that's where I want us to be from there. Somebody said, what will the tutorials be one-to-one? No, because I won't have time. You know, there's 66 of us in this triple only class, so I think we'll probably get, if we get maybe me with 4 or 5 people, and then we can put on, you know, the everybody can sort of join in, like almost like a Zoom meeting, so we can all sort of do our own sort of see each other and do it that way. If you want to, you don't obviously have to turn your camera on, but you will be able to ask questions other than just typing. So I'd invite you to like a meeting and give you the link and things like that. So we'll look to do that on next Tuesday, which is the Science Enrichment Day. I'm going to stick up a webinar. We'll have a bit of that in the morning. I'm doing some required practicals, taking lots of takes to try and get these right for you, which I'm going to finish off this afternoon, and I'll push those out to you as well. And then we can talk about what, you know, if you come to a tutorial with something you want to talk about, we can do it like that. I'm reluctant to say we'll do it on this, because people might think, well, I'm okay on that, and then actually, but I'd rather have done you know, something else instead. So if I only invite 5 people or 4 people to a tutorial, then everybody's got something that they want to go through, then actually we get quite a good session, you know, for sort of 20 minutes, half an hour or so, doing that. So I hope that's answered your question, and also made other people think, oh, brilliant, okay, then I would definitely sign up for those, and they will be on the Tuesday from that. Okay, so no other questions have come through, which is great. Always email me individually if you've got something that you just want an answer to, or you want to be sure of. And tomorrow I'm going to do a revision session at 11 o'clock. The webinar will be a revision session, but I think it will mainly be on some stuff on forces, to be honest, for the combined science section of it. So we'll just go back over Newton's laws and things like that again as well, just for half an hour. I'll just do a quick run through that you can look at, and then I'll push out some questions that will be forces, magnets and waves. Okay, that will take you about an hour and a quarter, well, maybe about an hour and a half or so, so you can work through those that week. So just to check, see how you've gone on with that. Okay, right, thanks everyone so much, everybody, for taking the time to join, and I will you'll see me tomorrow. Okay, bye.